I am A. Tausif Ahmad, leading to PhD degree course under the guidance of Dr. U. Rizwan, Associate Professor and Head, PG and Research Department of Mathematics, Islamia College, Autonomous Manembadi. My paper title is Testing Bivariate Overall Decreasing Life Aging Class of Lifetime Distribution Based on Moment Inequality. Outline of the paper: Introduction. Next, preliminaries: moment inequality, testing bivariate exponentiality against bivariate overall decreasing life aging class, and Monte Carlo simulation. Further, we extend with application to real life data. In conclusion, then reference, followed by reference. Introduction. Certain classes of lifetime distribution and their variation have been introduced in reliability. The application of these classes of lifetime distribution can be seen in engineering, biological science, maintenance, and biometric. The main aim of constructing new tests is to gain higher efficiency. Bivariate aging class of lifetime distribution is a new branch of reliability which is established by developing the measurement of success or failure concerning reliability. Bivariate distribution are observed in different practical situations. For example, in the survival of a paired organ such as a person, eyes, air, kidney, lungs, or in the survival of two-engine airplane. Testing bivariate exponentiality against some bivariate aging class of lifetime distribution has been seen a good deal of attention. For the moment inequality for bivariate overall decreasing life aging class of lifetime distribution can be found in the work of Satyaraj and Rizwan 2019. Now we propose a test statistic for testing bivariate exponentiality against bivariate overall decreasing life aging class of lifetime distribution based on moment inequality. Preliminaries. Let x comma y denotes the survival time of a device having a joint distribution function f of x comma y. The bivariate joint survival function is given by f bar of x comma y is equal to p of x greater than x, y greater than y for all x comma y is greater than or equal to 0. Here we assume that f bar of 0 comma 0 is equal to 1. That is survival function of your 0 comma 0 is equal to 1. Next, definition. A bivariate random variable x comma y or its distribution function f bar of x comma y is said to have bivariate overall decreasing life aging class if integral s to infinity integral t to infinity w at f bar of x comma y dy dx less than or equal to mu into w at f bar of t comma s for all x comma y t comma s is greater than or equal to 0. Here w at f bar of x comma y is equal to 1 over mu sum integral s integral x to infinity integral y to infinity f bar of u comma v dv du where mu is equal to integral 0 to infinity integral 0 to infinity f bar of x comma y dy dx denotes the mean of a bivariate lifetime distribution and it is assumed to be finite. Next, definition 2.2. The rth moment of a bivariate random variable x comma y is mu at r equal to expectation of x to the power r y to the power r equal to r square integral 0 to infinity integral 0 to infinity xy to the power r minus 1 f bar of x comma y dy dx. Next, moment inequality. A moment inequality is derived for the system whose lifetime distribution is bivariate overall decreasing life aging class of lifetime distribution. Next, we prove the theorem. Let f be a bivariate overall decreasing life aging class of lifetime distribution with the finite mean mu, then mu at r plus 3 over r plus 3 is less than or equal to mu into mu at r plus 2 for all r is greater than or equal to 0 and which is an integer. Proof. Since f is bivariate overall decreasing life aging class of lifetime distribution, we have integral s to infinity integral t to infinity w at f bar of x comma y dy dx is less than or equal to mu into w at f bar of t comma s. Multiplying both sides by ts to the power r and integrating we get integral 0 to infinity integral 0 to infinity t into s to the power r integral s to infinity integral t to infinity w at f bar of x comma y dy dx ds dt is less than or equal to mu into integral 0 to infinity integral 0 to infinity ts to the power r w at f bar of t comma s into ds dt, which is equation number 3.1. Then we considering the right hand side RHS of 3.1, we get mu at r plus 2 over r plus 1 into r plus 2. And when next we consider the left hand side of 3.1, we get mu at r plus 3 over mu into r plus 1 into r plus 2 into r plus 3. Using the equations 3.2 and 3.3, the inequality 3.1 becomes mu at r plus 3 over mu into r plus 2 into r plus 2 into r plus 3 less than or equal to mu at r plus 2 over r plus 1 into r plus 2, or mu at r plus 3 over r plus 3, which is less than or equal to mu into mu at r plus 2. This completes the proof of the theorem. Next, testing bivariate exponentiality against bivariate overall decreasing life aging classes. Using the previous inequality, we test the null hypothesis against the alternate hypothesis that h naught is, that is null hypothesis is f is bivariate exponential against the alternate hypothesis h1 is f is bivariate overall decreasing life and not bivariate exponential. We consider the bivariate exponential distribution introduced by Marshall and Alkin in 1967, which is f bar of x comma y equal to exponential to the power minus lambda 1 x minus lambda 2 y minus lambda 1 to maximum of x comma y. For all x comma y, lambda 1 lambda 2 is greater than 0, lambda 1 2 is greater than or equal to 0. Then we defined the test statistic delta t equal to mu into mu at r plus 2 minus 1 over r plus 3 into mu at r plus 3. Note that under h naught delta at e equal to 0, while under the alternative hypothesis h1 delta at e is greater than or greater than 0. And we considering the bivariate random sample from the distribution of lifetime from the distribution f, that is x1 comma x2 x3 comma x4 etc etc xi comma x at I minus 1 comma xi etc etc x at n minus 1 comma x at n. The estimate of delta at e cap of delta at e can be obtained as delta at e cap equal to 1 over n into n minus 1 into summation I equal to 1 to n summation j equal to 1 to n x at I into x at j to the power r plus 2 minus 1 over r plus 3 into x at I to the power r plus 3. To make the test statistic scalar invariant, let capital delta at e cap equal to delta at e cap over mu to the power r plus 3. Then capital delta at e cap is equivalent to the classical U statistic Lee 1989, and it is given by u at n equal to 1 over nc2 summation I less than j less than or equal to n phi of xi comma xj. The asymptotic normality of delta at e cap is summarized in the following theorem. Next, we prove this theorem. As n tend to infinity, root n into delta at e cap minus delta at e is asymptotically normal with mean 0 and variance sigma square, where sigma square equal to variance of xi into mu at r plus 2 minus 1 over n plus r plus 3 into x at I to the power r plus 3 plus x at z to the power r plus 2 into mu minus 1 over r plus 3 into mu at r plus 3. Then we prove this theorem from the standard theory of U statistic Lee 1989, sigma square equal to variance of chi of xi comma xj, where chi of xi comma xj equal to expectation of phi of xi comma xj such that xi plus phi of expectation of phi of xi comma xj such that xj, then which is phi of expectation of phi of xi comma xj such that xi is equal to x at I mu at r plus 3 minus 1 over r plus 3 into x at I to the power r plus 3. Expectation of phi of xi comma xj such that xj is equal to xj to the power r plus 2 into mu minus 1 over r plus 3 into mu at r plus 3, and thus we get the sigma square equal to variance of xi into mu at r plus 2 minus 1 over r plus 3 into xi to the power r plus 3 plus xj to the power r plus 2 into mu minus 1 over r plus 3 into mu at r plus 3. This proves the theorem. Next corollary, under H naught the limiting distribution of u at n is normal with mean delta at e cap. The variance of root n into un is a function of lambda 1, lambda 2, lambda 1, 2. Then we prove this corollary. Since the variance of root n into u at n is very complicated under H naught, and since u at n is a function of u statistic, jackinifying would not only reduce the bias but also enable us to estimate the variance of v of root n into u at n. The estimate of v of root n into un is v cap of root n into u at n, which is equal to n into n over n minus 1 summation I equal to 1 to n u at n comma I minus u at n whole to the power whole star whole to the power square, where u at n comma I is equal to u at n minus 1 into x1 comma etc x at I minus 1 comma x at I plus 1 etc x at n, and u at n star equal to 1 over n summation I equal to 1 to n u at n comma I. Using the result from Sen 1977, root n into u at n over variance of v cap of root n into u at n whole to the power half is asymptotically standard normal, which is equal to n of 0 comma 1. This proves this completes the proof of the corollary. Next, we develop Monte Carlo simulation. In this section, the Monte Carlo simulation null distribution critical point of delta at e cap are simulated based on 10,000 generated samples of size n ranging from 5 to 25 with the interval 1 and 25 to 60 with the interval 5, 60 to 100 with the interval 10. Table 1 gives the upper percentiles of the statistic delta at e cap for the different confidence level 90%, 95%, 97%, 98% and 99%, and the critical values of the test statistic delta at e cap is as follows. Then the relationship between critical value and the sample size for the different confidence level 90%, 95%, 97%, 98%, 99%. It is clear from table 1 and this figure that the critical value increases as the confidence level increases and almost increases as the sample size increases. Application to real life data. In this section, we consider an example given by Gross and Clyde 1975. The data are given in table 2, which denotes the length of the time required for patient with headache to achieve relief. Each patient receives a standard treatment and a new treatment on separate occasions. The times are recorded to the nearest tenth of a minute. This table appeared in Gross and Clyde 1975 in page number 232. We use our test to detect whether these times of the relief of headache for a standard and new treatments in minutes follows a bivariate exponential distribution with exponential minimum or not. The time of relief of headache for the standard treatment and new treatment. Here there are 10 parallel patients. They are giving the treatment on different occasion. For the standard treatment, new treatment. Next, the graph of relief of headache for standard treatment and new treatment as follows. Then Using the data in table 2, we obtained the value of the test statistic delta at E cap equal to 17.919306. Thus, root n into u at n over variance of root n into u at n whole to the power half equal to 7.917637 into 10 to the power 2. Hence, we reject H naught and conclude in the favor of bivariate overall decreasing life aging class of lifetime distribution. Then we accept H1. We shows that the property has we shows that the data set has bivariate overall decreasing life property but not bivariate exponential. Conclusion: the bivariate overall decreasing life aging class of lifetime distribution is considered the moment inequality is derived a new test statistic for testing bivariate exponentiality against bivariate overall decreasing life aging class of lifetime distribution is proposed based on the moment inequality. Using Monte Carlo method, critical value of the proposed test are calculated for n ranging from 5 to 25 with the interval 1, 25 to 60 with the interval 5, 60 to 100 with the interval 10 and tabulated. Finally, application to real life data is carried out. These are all the reference I have refers to prepare the papers. Thank you.